Okay, so this is a non-standard problem, because when you look at this 40, from here it's very difficult to move forward. You know that AB is equal to AC, and you know that AD is equal to AE, but from 40 it's very difficult to move forward. So this is a good example of where you give a name to a symbol like this. Let's call this Y. You got X here already, and then maybe we can move forward from there, right? So you give a name to an angle. This is a very useful trick. Now, if that is Y, because AB equals AC, that angle there is also Y. This is an isosceles triangle. And then you now have, in the small angle triangle, you got two angles. Okay. Now you can work out the third angle. The third angle will be, if you want to do it like that, it's you add X and Y and you subtract it from 180 degrees. That will be this angle here. Okay. Now there you use the angles of a triangle, but very often you will see, even in these problems, we use another theorem which is far more useful in problem solving, and that is the exterior angle of a triangle equals the sum of the interior opposite. Curl equals dot plus cross. Okay, I call this the flag theorem because there is really, you have to look for a flag like that. See, like you see here, and that angle there is the sum of these two. And in this example here, you can see the flag coming down like that, going like that, going like that, and there's your flag. And this angle here, which I'm pointing to, is the exterior angle. That will be the sum of these two angles, X plus Y. Right, which is a very happy place to be in, because you know that AD is equal to AE, right? And that's an isosceles triangle. So you have the base angle of this triangle is X plus Y, so therefore this angle here should be X plus Y. See, so starting from this angle here, for which you're given a name, we are moving from one point to the other. That's how geometry riders problems are, okay? Where you sequentially, logically, you make one conclusion after the other. So this is where we are. We got X plus Y, and this is X plus Y. Now you see that in this triangle here, you have an exterior angle. You see this here, this here is your flag, like that, like that, like that. And therefore 40 degrees plus Y, this angle here, that plus that, is equal to this exterior angle. Now watch, the exterior angle is, you have to, your flag is this, like that, you see. So the exterior angle is this whole angle here, and that is actually X plus Y plus X again, because it's that angle plus that angle, gives you this exterior angle. And now you got an equation. And that's the whole idea in mathematics. You somehow try to get to an equation, and then you use your school mathematics to solve the equation. So here the Y's cancel, and your 40 degrees is equal to X plus X. So X is equal to 20 degrees. Okay, by show of hands, can you please tell me, two people have got the answer? 3? Very nice. Okay, a fair number of you have got the answer. I'm very pleased. This was not an easy problem. You have to use. Okay, thanks very much, guys, for telling me that you have solved it. But the rest of you, please take note of the method in which we have used this to solve this problem. Okay, let's get to the next problem. Okay, so we are at the second problem. I just want to clear my drawings. And this is also a similar kind of a problem. It's a very simple diagram. You just put a single triangle and you got one line shooting through. and yet you have such interesting questions on simple diagrams like this. So let's read this question. It says in triangle ABC, there is a point D on AC such that AD equals DB. So again, we have an isosceles triangle here. The isosceles triangle being AD, oh, it's already marked here, so that's fine. AD equals DB. Okay, it is also known that this angle ABC minus ACB is 30 degrees. Okay, let's see. Before I go to that, I just want to do the same thing that I did before. I always like to use algebraic symbols, X, Y, and so on, because then you can do algebra with it, as we saw the last time. You can get equations and you can solve. And with things like this now, they hardly, can be regarded as equations that you can work with. So it's nice to use X's and Y's, and we will translate that thing here into X's and Y's. So where do we start? Because we know that this is an isosceles triangle, let's give a name to that. We'll call that X. Okay. CBD is what we're looking for. CBD. So that, maybe we should have given that X, but it doesn't really matter. Let's call it Y. Right. So the question here is, we must find Y. What is Y? Calculate angle CBD. So I've renamed it as Y, then it becomes an algebraic problem. All right, let's start here. You got X here, then this is an isosceles triangle, so therefore this has to be X also. Right. Okay, and there you've got it. You've got a Y here, and you've got an X here, and this also given that ABC, let's see what's given here. Let's translate this. ABC, okay, that's your X plus Y. That's ABC. ABC is X plus Y minus ACB. Minus ACB. We haven't given that any name. That's angle C, in other words. That's given as 30 degrees. So that is given, and we are putting that in the language of the symbols that we have been using. Now, ACB, that's angle C. This angle here, if you look at it, you see this angle and this angle here are two angles of this triangle, and that one is an exterior angle. So you got your flag here, you see, there it comes down like that. And you will see that angle C plus angle Y is equal to angle X. That's your exterior angle. Helen, I'll address you just now. Okay, so you got angle C plus angle Y equals X. And now we wanted to know what is this. This is angle C is actually equal to X minus Y. And you can make C the subject of this formula, which is the same as angle ACB. So you go back there and you get rid of this angle here by replacing it by X minus Y. And there you have it, you got your equation. So just as in the previous example. And the rest of it is now routine. You just use your school mathematics, open brackets out, and you have 2y is equal to 30 degrees, and therefore y is 15 degrees. So you use algebra and algebraic symbols, you can solve these problems very nicely, and they are very pretty symbols. Helen, you had a question?
Sorry, I just forgot to lower my hand.
Okay, no problem.
My Wi-Fi was a bit bad, so I didn't get the message.
Okay, no problem. Okay, I trust you are all happy with that. Is there anybody who got 15 degrees? Those who have got 15 degrees, show by raise of hands. Alexis, very good. I'm happy to see that there are learners who are tackling these problems beforehand. But there are not many. I see there may be just about a dozen, and we have almost about 80 or 90 students. Now that is not very satisfactory. Hopefully next week, most of you've got the questions now, You've got the questions and you've got the book. So you've got all the material. You don't need any further stuff. You try the problem, struggle along, and look at the notes that are given, and go and read the notes, and thereafter you can try to solve the problem. Only when you fail, you can go and look at the solution. We will do that just now to illustrate what we mean by that. Okay, so this is problem number 2. Let's go on to problem number 3. First, let me just clear all these drawings, and we go to problem 3. So problem 3, let's read this first. A shape consisting of 1,000 small squares. Okay, you can see a lot of small squares here, but obviously you don't have 1,000. I got an arrow here which is saying this is going on and on. Okay, so you have just 6 rows shown here, and it's got 1,000 squares altogether. So let's, as a starting point, even before I read the rest of the questions, let's just get a feel of this problem. You've got 1,000 squares altogether, and each row has got 5 squares. So that allows me straight away to calculate the number of rows. The number of rows is 1,000 divided by 5. Because each row has got 5, and there are 1,000 altogether. So there are now 200 rows here altogether. Okay, so that's a starting point. Now, if each small square has a side of length 1 centimeter, okay, that's fair enough. All these side squares have got 1. So these are all 1s here. Right. Find the perimeter of the whole shape in centimeters. Now, what do you mean by perimeter? Perimeter is the length across the boundary. So if you start here and you go in a zigzag fashion, come down to the bottom, climb up again, and go all the way, and you come back to that starting point. The question is, how far have you traveled? That is the perimeter. The length of the boundary of any region is called the perimeter. Okay, so let's start here and move along the boundary. Let me move like that. What do you have? You have 5 here. Right, and then I'm going to go down. I'll go down and then horizontal, down and horizontal. Okay, now that sort of complicates issues. So why don't I look at all the verticals? I'm going to just put verticals right through plus the horizontals. That is what we need to calculate. Okay, and there's also a 5 here at the bottom. Okay. Plus 5. I take the top 5, take the bottom 5, and now let's do the verticals first. So there's a vertical here. There's another one here. There's another one here. So each row gives you a vertical. And how many rows do you have altogether? You've got 200 rows. So you take all these verticals and you come right down here, and you have and each of these is 1 centimeter long, so it's plus 200. So there are 200 of these. There are 200 rows, therefore there are 200 vertical lines. Okay, now you go along this. Okay, that 5 we've already taken care of. And then you have the horizontals. Now the horizontal, you don't count this horizontal because it's already counted here. You can count this one. That one, that one, that one, and so on all the way up to this. Oh, wait a minute. There were other verticals on the other side. Yeah, sorry. There's actually 200 times 2 because we didn't count the vertical on the other side. So you got these 200 here and the other, another 200 verticals, all these verticals here. So that gives you another 200, so there are two 200s. Okay, now we're going to do the horizontals. And we start with this horizontal. That horizontal, that is on. You go all the way. You only go up to this point here because there's no horizontal for this. So there's actually 199 horizontals because this horizontal has already been counted here. And likewise, here, you got a horizontal here, you got a horizontal here. The first row contributes something, the second row contributes something, but the last one doesn't contribute anything. So there's another 199. The last one being the one there. So that takes care of the entire perimeter. You should count all the verticals and all the horizontals. And we have counted these. And that's the last 5 there. So there are 4 numbers to add. And you can go and get the answer. The actual answer is, what have we got? We got 400 plus 398, 798 is 808. So the perimeter of this 808 centimeters. Remember each side was 1 centimeter long. And let me just see again now, by show of hands, if you can just let me know whether you've got 808. Oh, now we got many more. Lovely, lovely.
Yeah, many more answers.
Yeah.
Good.
Okay, you are doing better and better. Well done. Okay, so those.
Prof, before you continue, I think some learners forget to put their hands down after they have answered. When you're busy explaining this, the sound always, the hands are up.
Oh, okay. There are 4 participants who have raised your hands. Are there any questions? 3 people have raised your hands. Do you want to raise a question? Okay, Tabelo, you have a question? Okay, I think he was answering the question that he worked the problem out. Okay, let's now get on to the next one.
Can they, Lindo,
when you're answering, please put your mic on, then I can hear you. If you need to say something and I ask you, then you can put your mic on, talk to me, and you can put your mic off. Now there are 2 participants who raised their hand. Can you please?
Pato?
Tabelo, you want to ask a question? All right, I think he's got a problem. Let's go on.
No, I don't know. Okay.
You okay, Tabelo?
Yeah, I'm okay.
All right, okay. Now you can take your mic off, please. Okay, now we're going to get on to the next problem.
Yeah.
Which is...
Can you also put his hand down?
Please put your hand down. Use that gadget there to click it again so that your hand is down. Okay. Okay, so the next problem is... This problem is quite a challenging problem. So pay careful attention. In many of these problems, there's a lot of thinking involved and very little calculation. See, that is the beauty of mathematics. Mathematics is a subject where it teaches you to think, not so much solving quadratic equations and all that. Detailed, long detail. Only occasionally you'll need to make a lot of detailed calculations. But in round 1, very few. You'll notice the only 2 major equations we had was 2x equals 30 degrees. And there's another one which was 2y equals 40 degrees. hardly any much mathematics. So this one here is another example like that. The adjacent sides on of the shape on the left are right angles to each other. The shape is divided into 3 pieces, cutting along the indicated lines. The pieces are then arranged into the shape on the right. Okay, so I'm going to go through some of these briskly because I expected you to actually do them before coming here. So if you look at this thing here is cut into 3 pieces. So let me just highlight those pieces. This is one piece, right? And then it's rearranged. You'll see that thing has gone here now. And then this rather awkward shape here is still there. You can see it. And then this triangle has been put underneath this. You see? It's put in here somewhere. And then you have this new shape. So this shape here has been cut into the shape of a triangle, and they all fit in exactly. Now you are given only 2 sides here. You're given this thing here is 11, that line there, and this thing here is 13. And the question is, what is that one? So that's the problem. Okay, as I said, this is quite a challenging problem. But if you really want to do it, what would be useful is to redraw this thing here into this shape. See? So I want to take this triangle and put it in here. Like that. And then join this. So this triangle, I've put it in fully here. And then also you got that this shape fits in exactly into this corner. So I'm going to, it's much more, so, sorry. So really, you're supposed to have something like that. And yeah, so there's your shape now. Okay, now that we got everything into the original shape, maybe we can calculate x. Now let's see, where is this? This 11, the 11 actually fitted inside here nicely. This 11 is here. This triangle has been turned around. So this side here is 11. Now this is 13, and then you got this. This thing here is the same as this triangle. Because this triangle here has been turned and put upside down here. So this other line here would be the same as this. But this can be calculated easily because this is 11 and this is 13. So this is 24. This line here is just the sum of 11 and 13. So once you know that this is 24, this triangle is the same as this triangle. It's just been cut and put elsewhere. So this now becomes 24. Okay. So that means this entire line here is 13 plus 24, right, which is 37. But if you look at this picture, this triangle here is the same as this triangle. And the x here is really, it's not the hypotenuse. This is 11, the x is the other side, and this picture tells it all. It tells you what x is. X is 13 plus 24. You see? What a simple calculation. Nothing very complicated. It's a grade 1 calculation. But you have to understand, all I did was took this and transpose it back there and use the given information, 11 and 13, to get the side and so on. And proceeded. Okay. Yeah, once again, let me ask you, is there anybody who got the 37? X equals 37? Oh, a number of people. Wow. Hey Patrick, we're going to get a lot of people going into round 2 here in this class.
Prof, I can tell you yes.
I mean, this is a hard problem. And look, I
never
expect
expected-
that many of these people who are raising their hands are the same people who raised before.
Yeah.
It means that they are the ones who have tackled the problems, right? And there's a large number. We've got 96 students here, guys, but a number of you are silent spectators. Now, this is not a soccer match in COVID time, where the stands are all empty, right? I want the stands to be full here. This is not COVID. So make sure next week you become better prepared, those of you who haven't been looking at it. Okay, there are 2 people who raised their hands. Do you have a question? All right, if you haven't, please put your hands down. Okay, so this is a question. You have to try this thing out, please. Let's just quickly see what it says. In rectangle ABCD. Now, very often they don't give you the diagram. So you'll have to draw the diagram yourself. Unlike in school mathematics where they pamper you and give you the diagram. Here in Olympiad mathematics, you're expected to draw the diagram yourself. So let me just take you through this because very often, maybe you don't have any experience in this thing. So I'll just take you through the diagram. But in future, I'm not going to draw the diagram for you. So you draw a rectangle. Right? And the rectangle is named as ABCD. So we can name it. We can name this rectangle. BC is the longer part. So let's just make sure that the BC is 11 and A, B is 6. So now you have A, B, C, D. When you're naming it, don't go A, B, C, D like that. You must go in one direction, right? Otherwise, you'll get a wrong diagram. Okay, then they say F and E are points on AD. So F is here somewhere. It's a point here. And what else do they say about F? They say that CF bisects angle C. So there's C here. And that is going to bisect. Your CF bisects this angle. It divides that angle into 2 equal parts. And likewise, AD on this side bisects this angle. Okay, so that is what you've got here. You've got that these angles are bisected, which means that these angles are equal. Bisected means they are equal. So that's the information you've got. And this point here is D. And this point is F. And the question is, what is the length of EF? Oh, there's something wrong here.
Yeah, F and E on the same line, AD.
Yeah, okay. Sorry about that. Let's just.
Prof, you bisected A instead of bisecting B.
Oh, okay. Thanks for that. Let me clear.
I thought I told you to the wrong.
Sorry, I wasn't reading the question properly. Okay, there's a lesson. Always read your question properly. Don't do what I do. Okay. So let's just bisect this angle here. So there's an E down here. I think that is what we want to get to. So there's an E. It's BE, yeah, right. BE and CF. All right. And the question is, what is EF? Right. Over to you guys. Let's see whether you can calculate EF. You got a rectangle. You got the 2 sides are 6 and 11. And you are asked to calculate. Put your mics off. as I become more and more efficient in this contraption, I find that I can go faster. Right, so I think we're already there. I just have to name everything. Okay, so you got EF. I think we had F and E here, and we had B and C. There was B here. B here, and C here, and A and D. All right. So Ray, you said FE is 1. Can you please explain?
Yes, Prof. Just also A, B, and C, D is equal to 6 centimeters.
Okay, let's put 6 there.
Because it's a triangle, we know that triangle BAE is a right angle and BCD is also a right angle. Oh, so not that. Yeah. So we know that we can work it out using Pythagoras. I know that because BE bisects B, we know that it's 45 degrees both sides.
Yeah.
And beforehand knowledge, I know that tan of 45 equals 1 because it's a special angle.
Yeah.
So using that, we can say tan of 45 is equal to opposite over adjacent, which is AE over 6.
AE over 6, yeah.
And that means that tan of 45 times 6 equals AE.
Yes.
Which is equal to 6.
All right, I'll just stop there for a moment. Now, this is a good example where you use a machine gun to kill a fly. You see, this is 45 degrees, 90 degrees. So this is 45, Ray. So you got isosceles triangle. AB is equal to AE because these angles are 45. Therefore, this is 6. Okay.
Okay, sir.
All right. And Ray, you want to say maybe the same thing happens on the other side?
Yes.
Yeah. But what about this angle here? What is this angle equal to? Oh, that will also be 45 because this is 45. This is 90 here. So this angle is 45. So again, for the same reason, you got this whole thing here is equal to 6. Is that right?
Yes, Prof.
Okay. Now how do you get to FE?
I made a simultaneous equation. I stated that A plus E is equal to 6 centimeters.
Mm-hmm. AF plus
and
E.
Yes, and A plus. Wait, I just can't see the question. I also said that.
You go. Okay, stop there. You go. You. From this point onwards, how do you go? Put your mic on. You go. All right, he's not communicating. Ray, what I would suggest is do what I do all the time. This is an unknown. Give a name X to it. In maths, give names to unknowns, unknown angles. Give names and use algebra. Then once
yes,
you use X, then immediately you can get that this is 6 minus X because the whole thing is 6.
Yes,
and again,
I was gonna say
this whole
that.
thing is 6, and if this is X, then this is also 6 minus X, right?
Yes.
See, so you use algebra and you move forward, and now you got this whole line here. And what's the length of this entire line?
11.
11. So you got an equation. That's the goal, to get an equation. The 3 pieces add up to 11. The plus here. Okay, and that gives you X equals 1. You can work it out. It's a simple equation. Thanks very much, Ray. All right.
Thank you, Prof.
I hope you guys understood it. The important thing here is that you got 45 degrees here, and recognizing that whenever you got a right angle triangle with one of the angles equal to 45, straight away you got an isosceles right angle triangle, right? The sides are equal. So that's what we exploited here. Twice we did that. And then the trick was to give a name to the unknown. Right? Don't use some simultaneous equations and get a. If you do AF plus FE and so on, you know, I mean, it says nothing. Use X's and Y's. They are much more familiar objects. All right. Anybody else got one there? Okay. A number of you. Okay. Thank you very much. Okay, now let's get on to the next problem. And it seems to me that the next problem is also something that you have to do. Right, this time you draw your own rectangle. All right. I recall those midpoints here. Sorry, I'm taking too long over this because I'm trying to recall what I did and I can't recall it. So you got OABC is the rectangle and M is the midpoint of BC, CB, as you can see, and I've shown it here. This line should be a little bit more, and then this is should be there. Okay, and then what else do you have? P lies in AB so that BP is equal to 3. So you got a point here, P, like this, and this is 3. The length of OM is 17. And the problem is to calculate the length of OP. Oh, God forbid. The problem is to calculate the length of OP. Okay, so that is the question. And let's see what Alexis has to tell us.
So firstly, we have C and B, which equals 16. It's given in the question. So that means M1 and M2 is 8. Owing to the bisection.
Okay.
Now, by means of Pythagoras, owing to the right angle triangle, you'll get OE, which is 15.
Okay, so okay, I think you have different symbols. OM was 17, and this is 8, and therefore you calculate this one here, is it?
It's 15.
Yeah, because the right angle triangle using Pythagoras. How do you know it's 15, Alexis? Calculate use a calculator?
Excuse me, so I just used Pythagoras, so it's 17 squared minus 8 squared, and that should give you 15 squared.
How do you know?
And then,
how do you know it's 15 squared? How did you calculate it?
So I used the square root sign.
The square root sign. Oh, you use a calculator?
Oh no, sir.
You use
So
a
I know
calculator. Naughty girl. Not allowed to use calculators. I'm asking this because you don't need calculator. Watch this. Look what I'm doing here. A squared minus B squared is A minus B into A plus B. 17 minus 8 into 25, because 17 plus 8. And the square root of that is 3 times 5. How's that, guys? No calculator, huh?
Cool, sir.
Cool, man. Right. Okay. Okay, so you are at 15. So this part here is 15, right, Alexis?
Yes, sir. So that means AP is 12.
So the AP is 12, yeah. And there we are. We're home.
Yes,
the two
sir.
sides of this. So therefore, you should be able to get the third side, which is 20. Now this time you can't use this one here because you don't have the hypotenuse. But this is almost like the 3-4 triangle, 3, 4, 5. That's a well-known triangle. So therefore 12, 16 will have to be 20. Okay? So
Prof,
the answer is 20. The three of you who said it's 20, that was quite right.
Yeah.
Well,
Helena's got a question.
Yes, question.
Helena's got a question.
Yeah.
When not told like which side is longer, for like OABC, it doesn't specifically say OA is 16. Does it matter which way around you work? And if then, is there a formula for which corner gets which letter?
That's a good question, Helen. You see, when they say length, usually the length is the longer side. And I think from primary school, you are told the length is the longer side. It is more of tradition than anything else. So if you say the length is 16, then you call that 16. Well, actually, it doesn't really matter whether it's, if you follow this thing here, whether it's the longer side or the shorter side doesn't really matter, because eventually you're going to get that the other side is going to be 15. Like you calculate it to be 15, so that would be the shorter side. So automatically, you don't know whether this was the longer side. Only after you calculate the other side will you know whether this is the longer side. So it's really immaterial. It doesn't really matter. It doesn't affect the solution. Is that okay, Ellen?
Okay, thanks. Yeah, thank you very much.
Right. So let's get on to the next problem. The next problem is I like geometry. Do you? Do you guys like geometry?
Not as much as regular algebra, sir.
You like your
Yes,
algebra?
prof. I like geometry, prof.
Yeah. When you see the really nice problems where you have to use your real skills, intuitional skills, then you see the beauty of geometry. Well, I of course I like everything, but I always got a preference for geometry. So I think we are at this one here now. This problem. What is the biggest possible area of a quadrilateral with sides 1, 4, 7, and 8? I'm doing this problem because this is a challenging problem. So there are a couple of lessons to be learned here. I've got a quadrilateral. So let me just draw some quadrilateral. Quad. Often we're too lazy to say quadrilateral. 5 syllables. So they say quad. So the sides are 1, 4, 7, and 8. I don't want to put the sides down here because we don't know what order it is. I could have had 1 and 4 here, 1 and 4 there, and they will be different quadrilaterals. The point about this is that there could be many quadrilaterals. There's not. If I got another quadrilateral with sides 1, 4, 7, and 8, it might be looking very different from this. They are not congruent. 4 sides is not a condition for congruency in quadrilaterals. In triangles, 3 sides is a condition. That means if you're given 3 sides, all triangles with 3 sides are 3 given sides are exactly the same. But here you can draw lots of quadrilaterals having sides 1, 4, 7, and 8. Okay, so now that is why they say, what is the largest possible area? There can be many triangles, but amongst quadrilaterals, but amongst all of them, you got something which has got the largest area. All right, so let's do this. The way to do this now, I'm not going to put down 1, 4, 7, and 8 because I'm not sure where these numbers sit. I'm just going to use A, B, C, and D, knowing that these numbers are those numbers. I don't know exactly in which order they appear. Now the question is to find the area of this quadrilateral, and we are given A, B, C, and D. So how do you find the area of a quadrilateral given the 4 sides? Well, to this end, let us just draw a diagonal, and the diagonal would be a construction. So I'm just going to put that in another color to show this is a construction. Because if you split your quadrilateral into two triangles, then you can find the area. Okay, but even now I want to go two sides, and how do you find the area? Okay, now you guys are in grade 10, 11, and 12, and some of you, if you're in grade 11 or grade 12, you would have seen this formula. If you got two sides of a triangle and the included angle, it's called xy, and the included angle, then the area of this triangle is half xy times sine of the angle included by the two sides. Okay, I don't know how many of those who are in grade 10, you just started grade 10, you probably don't know anything about the sine, but just take it from me, you might learn something just now. Because if you find the area of a triangle, how do you find the area of a triangle? The formula that we already know for the area of a triangle is half base times height. So if I give a name to this height, then the area is actually equal to half base, use the symbol y, times the height. So that's the area. But now, if you look at this triangle here, right? The sine, what do you mean by the sine? The sine of an angle in any right angle triangle is opposite over hypotenuse. So the sine of theta here is opposite, which is h. That's the opposite, over the hypotenuse, which is x. Right. So now that gives you h. You can make h the subject because it gives you that h is equal to x times sine theta. Right? H over x is sine theta. So if you put your h inside here, you get x times sine theta. So you get half y x sine theta, and that's exactly what we said in the beginning. Half xy sine theta. All right, remember sine is opposite over hypotenuse, and while we are there for the grade 10 students, if the sine is opposite over hypotenuse in a right angle triangle, it's just a ratio. The sine is a ratio of that over the hypotenuse. Now you know the hypotenuse is the longest side, so this must be smaller than that. So the sine is a proper fraction. It's a fraction of a number over a bigger number. So the sine is always less than 1. So that's I need to know that the sine of any angle is always less than or equal to 1, because it's a smaller side over the larger side. So bearing all that in mind, so if you need to work out the area of this quadrilateral, the area is, let's give a name to this. Let's call this angle alpha. Let's call this beta. Then what do you have? The sum of the area of the quadrilateral that we're looking for is the sum of two areas. This area, which I just spoke about, is half AD, these are the two things, times the sine of the angle between them, which I've named alpha. And likewise, this other triangle, its area is half BC times sine of the angle between them, which I've called beta. It's the Greek letter B. So there's your area that you're looking for. And I told you that you're looking for the largest possible area So these are all given. A and D, they are numbers 1, 4, 7, and 8. They're all given, right? But I don't know where they are sitting. But we don't know about angle alpha and beta. But we do know that the largest possible value for sine alpha is 1. Right? The largest possible value for sine alpha is 1. And that happens when the angle is 90 degrees. So what does this mean? It means the largest possible area occurs when the alpha is 90 degrees, in which case sine alpha is equal to 1. Okay, so you have that these angles are actually 90 degrees. It doesn't look like 90 degrees, but now that we know it, we'll just put it down like this, and let's pretend that angle there, which is almost falling down, is 90 degrees, and this angle here is also 90 degrees, because these were your alpha and beta that we chose. So for the largest possible area, this has to be 90, and this has to be 90. Okay, so now that allows us to say what A, B, and C, D are possibly. All right, let's just go back to this. Remember that we just put symbols for these to conclude that the largest area occurs when these two angles are 90 degrees. Now, is it possible? We need to put in our numbers 1, 4, 7, and 8 here. Now, by Pythagoras, it means that this red line is equal to this squared plus this squared. And the same red line squared is that squared plus that squared. So we need to have that a squared plus b squared equals c squared plus d squared. You know, when we name these sides A, B, C, and D. Now that asks this question here. Can we choose A and B now? If you square all these, 1 squared, 16, 49, 64, can you get the sum of these two squares equal to the same thing? Yes, you see 49 and 16 gives you 65, and 1 and 64 also give you 65. So it is possible to have this situation. You'll have 1 and 8 to give you 65, and you'll have 7 and 4 to give you square root of 65. So this is a possible scenario. And so now that will give you the quadrilateral with the largest possible area. And now it's easy from this point onwards, because the area of a right angle triangle, we know it's half base times height. So 4 times 7 divided by 2, and 8 times 1 divided by 2 is 4. The largest possible area is 4 plus 14, which is 18. Okay, so this is, as you can see, this is quite a challenging problem. And are there any questions? We had to go out of the box and develop some other ideas before we came to solve the problem. And the idea was actually to find these angles here to make it the largest possible area. And we showed those angles have to be 90 degrees, right angles. Okay, so the next question is okay. This is a problem that I will have to work out because it's not in red. So what does it say? It says that a square ABCD has sides of length 6 units. One of my students last year, I don't know who he was, who told me the trick of how to draw squares using this gadget. To him, I am eternally grateful. All the sides are 6. M is the midpoint of AB. We'll put it here. M is the midpoint of AB. So let's just call this AB. And P is a variable point on BC. So P is a variable point on BC. In other words, it's not fixed. We don't know where P is. It's somewhere along BC. And the question is, what is the smallest possible value of dP plus PM? So let's see where dP is. dP is that line. So you're adding that and PM. Oh, M was midpoint of BC, not AB. No, that's right. M is the midpoint of AB. Okay, that's fine. All right, now this is a really hairy question, because how the heck are you going to find the smallest possible value for dP per PM? What this means is that no matter what P is, you calculate dP and PM, get an answer, move P, dP and PM, get another answer, move P again, dP plus PM, get another answer. You can go up to B. So the question is, what is the smallest possible value of dP plus PM? If I started at C, if P was at C, what do I have? If P was here, then dP would have been 6. If P was this point, if P can be anywhere here, then dP would have been 6. And PM would have been from here to here. PM would have been that. And there you got to, oh, by the way, this is 3, because this is the midpoint. So there you would have, the whole thing is 6. 6 squared plus 3 squared is 36 plus 9 is 45. So you have 6 plus the square root of 45. If P was this, then dP plus PM is 6 plus square root of 45, which is, for square root of 49 is 7, so just slightly less than 13. Some number smaller than 13. Okay. So how does one go around solving this problem? Okay, so there's a trick that we need to do on this, and it's not easy to see. What we have to do is you try to put dP plus PM into a straight line. Okay, and this is what I'm going to do. Let me draw a little smaller figure here. Okay, and then what we do is the following. You see, you take any point P here, and I'm going to draw my DP, and I extend this line here. I extend this line. And what I do is I reflect this line here. You find another point on this line which is also 3 units away. You see, if you don't know the solution to this problem, if you haven't seen it before, it's almost very, very difficult to solve it. So this is, you have to know that this is how you solve this kind of a problem. I take another point which is 3 units away from here. Right? Then I join this. Okay, and now the important thing is that these 2 triangles are congruent. I'm talking about this triangle here and this triangle here. Now, why are they congruent? Well, for one thing, these are equal because we said they are 3. And then this is 90 degrees because we're working with the square. So these 2 angles are equal. And you got a common side. Right? So these 2 triangles are congruent. So the PM that you're looking for, these are the 2 numbers that you're looking for. DP plus PM. There's DP. There's PM. Okay, we'll put a double tick there. But this PM is the same as this, you see. Because these 2 triangles are congruent. So when we're adding this click and this tick and double tick, it's the same as adding this and that. And you want this sum here to be as small as possible. That is the thing. There's a P here and a D here. There's a new number, let's call it N, a new point here. And you want DP. Now you see, as P varies here, which point P will give you the smallest possible sum for DP plus PM? And the answer is, it will have to be the straight line that joins D and N. That straight line will give you the shortest possible sum. Because when you draw, forgetting this, let's just draw this thing. So when you take the straight line, this P, if P was here, then DP plus PN is smaller than this thing here because this is a straight line. The straight line is the shortest distance between 2 points. So if P was here, then this length is shorter than DP plus PN. So, and if you can do this, no matter where P is, you'll always see that the straight line is the shortest between 2 points. So the point P that you're looking for is really here. That point P will give you the smallest possible sum for DP plus PM. Okay, I'm going to just take out all the other things in this diagram. Okay, and so now what is the smallest possible sum? The smallest possible sum is dn. That's the shortest distance between 2 points. Right? Now we already know that this is 6, and we know this is 90 degrees, and therefore dn is the hypotenuse of a right angle triangle. See, now this is 9 and this is 6, so it's just simply 6 squared plus 9 squared. So that is the shortest possible value you can have for dp plus pn, And that shortest occurs when P is the intersection of that line which we chose to this. Okay, it's a hard problem. If you haven't seen this, this is level 7 or level 8 problem. Okay. So I wanted to put a couple of challenging problems here also. If you didn't understand it too well, you can go and look at the relevant question. I haven't got the number here, but it is there on the assignment or the problem set which was sent to you. You can go and look at the number there. Right, do this one here. The diagram is there. And see whether you can solve this problem.
Hello?
Yes, James?
Okay.
Yeah, tell me why it's 80, James.
Sorry. Okay, so angle PCQ must be 142 degrees since angles on a straight line equal 180.
Okay, PCQ, yeah. Okay. So that's 142, you say, yeah?
Yes.
All right. Right, okay.
Then PAQ must be 138. So
Okay.
angles on a straight line equal 180. Then if we look at the quadrilateral PAQC, we know that all the interior angles must equal 360 degrees. So
Right, so the four angles all add up to 360 degrees. So P plus Q, that's what we need to find, eh?
yeah,
Angle P plus Q plus these
280 degrees together
280 degrees gives you,
equals 360. So
therefore P plus Q.
is
Right, very nice. Okay,
Prof,
yeah.
I did it slightly differently.
Okay.
So I constructed PQ, a line called PQ, and then I used exterior angles of a triangle.
Okay, the flag theorem. What I call
Yes,
the flag theorem. Okay, so what Luke did is he just joined PQ. That becomes a construction. I like to put my constructions in a new color because that wasn't there in the beginning. And then how did you proceed from there, Luke?
Well, I named them X1 and X2
Okay,
and
so
Y1
you named all
Y2
these angles here.
respectively.
So you're looking for that plus that plus that plus that, isn't it?
Yes, Prof.
Yeah, you're looking for all the sum of these four angles, but you already know that the sum of these two is 42.
Yes, Prof.
And you know that the sum of these two is 38.
Yes,
That's a
Prof.
flag theorem. You extend, therefore the sum of the whole 4 is 42 plus 38, which is 80. Okay, good. Look, that's that's a solution that I used, which I think is very elegant. All right, the next one is number 13. Let's just get to that question. This is also something that you can try. Try this problem, please. All right, let me take you out of your misery. Please pay attention. I've got the diagram here. The important thing is that this large triangle is isosceles. I didn't draw it as isosceles. It doesn't look like isosceles. So which means that if this angle is x, then so is that. And they're opposite equal sides of an isosceles triangle. But now you got this line is parallel to this. So this angle here is x because it has to be the same as this angle here. They are corresponding angles. Okay? Which means that this small triangle is isosceles. So this is also this is 15. See? No, I'm not. Sorry. Yeah, 15. This MA is the same as MP. So where I got MP, I'm going to replace MP by MA. And likewise, this angle here is equal to this angle here. Because again, you got parallel lines and you got corresponding angles. So this angle is also x. And that will make PQ equal to QB. So wherever I got PQ, I can put QB. QB. Okay, so the perimeter, which I've written down here, the perimeter is the sum of the four sides of this parallelogram. And we replaced two of those sides because of isosceles property. So let's have a look at which four sides, what we've got here now. So this MP was really MA. Okay. So now we've got PQ. Where is PQ? PQ, right there it is. Let me just shade that one. Let's use another color. So there's PQ. QC. There's QC. Oh, no, PQ is now QB. Right, so it's QB. Sorry. And then QC. CM. And MA. So these four numbers are nothing else but the sum of these things which I've shaded here. And that we already know is 15 plus 15. So two of the sides have to be replaced. And when you do that, you see you got those four pieces are here on the sides of the triangle, and we already know that these are 15 each. Okay? All right. Let's go on. We'll do the next problem. I have quite a few problems, but I don't have time to go through all of them, unfortunately. So I have to pick and choose. I wouldn't do this. You can try this one here. It's quite an easy problem. That is why I got it in red. I'm sure most of you will get it. This was a challenging problem, and I think it will probably be the last problem that I will tackle. The problem goes like this. ABCD is a rectangle with AB equal to 8. Well, of course, fortunately the diagram is given here. AB equals 8 and BC is equal to 14. So that is 14. A strip of width 2. So you can see a little strip here. The width, in other words, the width means these are perpendicular here. Has an edge on AD, as you can see, one of the edges is on AD and the other on BC. Determine the maximum area of the strip. See, very often they ask you questions on maximum area. We've already seen this a couple of times. So and we've got some strategies to solve this kind of a problem. So hopefully we'll be able to pick up a few things. Let's make this black. Okay, now the maximum area of the strip. If you look at the strip, it is a parallelogram. So the question is, first, to find the area of a parallelogram. Now, what is the formula for the area of a parallelogram? I think we have only one formula. Area of a palm. Anybody knows?
Base times height.
Yeah, base times height. See, unlike a triangle says half base times height, but for parallelogram is base times height. So in this particular triangle, there is already an height here. And the base would have to be this one here. Let's call this B, this line here. So we need to work out 2B. Because this is the base times height. Some of you might debate on whether the palm is 2B. And then you will ask the question, 2B or not 2B? Right, so this is where we are, with apologies to Shakespeare. And here, in other words, if you want to find the maximum area, you must get the maximum value for B. Right, so in other words, of all these lines that you draw with the strip here, you want one to be as large as possible. So evidently you're going to start here, right? And you're going to make this line as large as possible. So you're going to go, but you're going to create a strip, you see? So you need to go somewhere. You can't go here because you don't have any strip. And at the same time, you have to remember, this thing has to have a height of 2. So let's just say that is going to give you the largest possible area. So let me just complete this thing. Okay, and now we are going to say that this strip here has got the largest possible area, and what is the area of that one? And how do we go around doing this? The only thing is we don't know where we were supposed to finish off here. See? How far must I go? See? Obviously the strip will have to be like this because you want this thing here to be as large as possible. And the B is, you can see it's going to be looking like that. Okay, so now you need to work out what this X is. Okay. How does one go around doing that? You got the AB is equal to 8, and you got BC is 14. So the sides of the rectangle are 8 and 14. I've got this to be X. So you agree that this is going to be 14 minus X here. From here to here. Okay, and we already know that this is 8, opposite sides of a rectangle. And then you've got the height of this rectangle is given to be 2. Okay. Now we've got the rectangle is split into 3 pieces, but we know the area of the whole rectangle. The area of the rectangle is 8 times 14, because we know the length and breadth, right? So the area of this rectangle is 8 times 14, and now you can get an equation because that area is a sum of 3 areas. Right? This is also X here because this is a parallelogram. Opposite sides of a parallelogram are equal. So this will also be 14 minus x, because that is 14. So what is the area? The area is a half. We need to work out the area of this triangle. It's a half 8 times 14 minus x. So you got that area. But if you look at this, it's exactly the same area. So you're going to add those two. So you're going to multiply that by 2. And then to that, you're going to add the area of the strip, which is the area of a parallelogram, and that's 2b. Okay, so now the question is, now how do you work out b? Well, you can work out, okay, let's just do this. 2 times half is 1, and here you got 8 into 14 minus x plus 2. On this other side, you got 112, and the b is square root of, it's a hypotenuse of a right angle triangle, so I can replace it by x's, because it's 8 squared plus 14 minus x all squared. That's the other side, and you're working out the square root of those, the sum of those two, to apply Pythagoras. And there it is, you got your equation involving x. It's not a very nice equation, a pretty unpleasant equation, and it's a kind of an equation that in actually it's not too bad.
Prof, the time is up.
Time is up. Oh, time is up. All right. Now,
Please, Prof.
what you can do quickly is you get 8 times 14 is 112 here, and that 112 will cancel off, and then you have this equals, and you bring the 8x to the other side, and you have an equation like this. That's much more easier to solve. Then you have to square on both sides, all right, and then you have a quadratic equation, and with a quadratic equation you can find the roots and you can solve for x. And once you solve for x, right, then you can solve for b, and once you solve for b, because you use Pythagoras, then the area that you're looking for is 2b. So this is a challenging problem, number 15, and there are other problems. You can go and try these problems now. We were supposed to do it, but we didn't have enough time. But I always like to have a few extra problems, that just in case we don't want to finish early. Thank you very much, guys.